sense. Statistics is wonderful, but it really is a toolbox. And I'm reminded of this whenever I watch my 7-year-old try to use my tool sets. When he sees me out working on my bike, he always wants to help, which I love. But I see him grab a box wrench and go, "Daddy, I want to help you fix your bike." And then he grabs the wrench and starts smacking at my wheel with the box wrench. I'm like, "Buddy, let's talk about where you use a box wrench." So to draw a parallel, what I just did on this scatter plot was I took the box wrench, i.e. the best fit line, and I slapped it on something that doesn't look linear. Now, I can do that, of course. I can put a best fit line on that graph, but it sure doesn't look linear, does it? It sure doesn't look linear. Why does it not look linear? Let's go ahead and take this line off because it's probably driving you nuts to have it there. Go ahead, Amy. Or Amber, whoever's go ahead.
I was going to say the rate of change
is
not linear.
Is not good. Thank you for using that word. The rate of change. I want to keep that going all term. The point of the different kinds of modeling I want to do is that it's all about rate of change. The rate of change for me on my bike going down that hill is not the same as the rate of change, for example, me on flat ground pedaling consistently. Or me in the pool today. I was ridiculously consistent today. We did a 3,000 meter swim as a part of a fundraiser. 56 minutes. I almost did each 1,000 in exactly 19 minutes. I can't believe that. I thought I'd slow down ridiculously by the end, but I was almost spot on. So my speed in the pool today was linear, which I was not expecting. I was expecting a decrease. But this is totally expected on Earth. Why is that? Why do you expect this, Chrissy?
Because when you're trusting gravity to pull you down, what's it called, momentum.
Momentum. People's envy, baby. People's envy. Momentum and velocity are directly related by your mass, which means you will increase to a point. To a point. You won't keep speeding up. There is something called terminal velocity. I've hit it on my road bike coming down from Bachelor, but it's only a function of the steepness of the road. I've hit about 55, 60 coming down from Bachelor, and I can't get going any fast. I don't want to either, because if I crash going that fast, I'm going to die.
Yeah.
But there's a point, but if I could somehow shrink myself down even more aero, I'd go faster. I mean, the land speed record on a bike is something like 120 or 140 miles an hour. I mean, it's ludicrous. What's that?
Is that New Zealand on that road?
I would imagine it was a Kiwi. Oh, no, it's a volcano, actually. I think that dude did it down not on pavement, which I guess if you crashed, it might be better on dirt, maybe. I don't know, going 140 though. But the point is that if you're only under the force of gravity, you're going to pick up speed if that's it. And that's why I was very careful about not pedaling. I didn't want to add to that for it. I wanted to see only, as much as I could, the effect of gravity on my speed. Yes. Now, so one of you mentioned speed about 15 minutes ago. The whole point of this experiment is, I want to know how fast I was going. Because I'm tight. I want to know how fast I was going when I passed that group at 200 feet. That's what I want to know. I want to know how fast I was going. So I'm ready to take some guesses. I'm going to put them on this back board back here. We're going to start working towards a solution today. So how fast do you think I was going when I crossed that 200-foot mark? Throw it out there. Speed at 200 feet. Give me some ideas.
220.
Say it again.
220.
220, what's your unit?
I can't read it.
Feet per second?
Yeah, it sounds good.
Oh, I don't know what that is in miles per hour. Let's get that in miles per hour. Use Google. Yeah, you can do all kinds of fun conversions in Google, which is great. So 220 feet per second in miles per hour. If I spelled everything right, which I don't think I did. No, it doesn't matter. Oh, God, no, I wasn't going that fast. Oh, duh, silly me. I don't think you meant 220 over a second. You meant 220 over 10 seconds, I bet.
Yeah.
Because I would have had to cover that entire distance in 1 second. So let's call that 15 miles per hour. Let's call that 15 miles an hour, Ashley. That's okay.
Can't really see it.
That's okay. 15 miles per hour. Give me some other guesses. How fast was I going? Gut feeling.
13.4.
13 miles per hour.
Put it out there.
Put it out there, good. What I'm curious to do is see if you guys can capture an average. I don't know. We're going to see. Other guesses?
18.
18. Good.
75.
75. Why not?
Good job.
Why not?
That's
The few times I've gone over 55, you've scared the crap out of me. Say again. How about 6 miles per hour? Love it. That'll offset the 75, maybe. Good.
Yeah.
Balance. 2. Okay, I was just being silly. So the question I have is, how fast was I going? Could we calculate it? And this is a related question. It's a related question. How many of you have been on the road and you go by a police officer and we've got the hairdryer out the window winning at you and you go, crap, slow down, but it's too late because he comes out and he's going to pull you over. It happened in front of me today on the way into work. Coming out of the pool, not me, I wasn't going that fast, but the car behind me got pulled over because the hairdryer was out. He was sitting on one of those little side roads off of Newport with the hairdryer. And I heard the car behind me, the brakes come on. I'm like, oh boy. You know, going down Newport, God knows how fast. I went 25 right there. So, how does that little hairdryer know how fast the car is going? Josh.
like a form of echolocation.
Explain echolocation.
It sends out like a click, and then it tracks how long it takes the click to bounce back.
How would that tell you how fast the car's going?
I don't really know.
Good! You will after today. That's good. That's all you know. That's all you would expect to know. What you'll know is by the time we're done Wednesday, you'll know how echolocation works and how the hairdryer works. And now partially how GPS does, but it's not related in the same way. You definitely will understand how the hairdryer and the cop's holding works. Thank you, sir.
Feet in the seconds it returns?
Say that again.
Does it do feet, like the distance, and then the seconds it returns back?
But you need 2 points.
Okay.
You need 2 points.
How much time does he need to decide he's gonna pull you over?
Oh, that varies from cop to cop.
Yeah.
It also goes, he's going 9 over, that's fine.
Yeah.
There's all kinds of other wiggle room in there. But what I want to understand is what the mathematics is behind the hairdryer. And believe it or not, it has to do with this curve right here. It has to do with this curve. Now, not every car is going in that pattern. Not every car goes in that pattern. Obviously, some cars are going pretty linearly. Cruise control, for example, guarantees that. You put cruise control on, boom, 60 miles an hour, up 97, boom, to Portland, boom, 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 you're good to go. I would take it off through Redmond and Terrebonne, maybe. But, you know, for the and Madras. But for the most part, on the open highway, you put yourself on cruise control, you're not accelerating, you're not decelerating, you're constant rate of change. But, can we analyze this mathematically? I think we can. I think we can. Actually, I know we can. Please, Ashley.
Does that anything to do with maintenance law of refraction?
I don't know what that is, but give it to me and explain that to me.
It has to do with light and when it hits.
Oh, refraction.